In this video, we will discuss electric potential energy. More importantly, we want to differentiate two different forms of electric potential energy. The first is the electric potential energy of a system of point charges, and the second is the electric potential energy of a particular charge in an electric field due to other point charges. To understand how to calculate electric potential energy of a system of point charges, let's look at the following system. In this system of point charges, you have 3 point charges. The first one is a negative charge located at a coordinate 0, 4. So the y-coordinate of that negative charge is 4. It has a strength of -1 microcoulomb. The second charge is the positive charge on the left. The x-coordinate of that charge is -3, and the strength of it is +2 microcoulomb, right there. And the third charge is a positive charge at x equals to 3 with a strength of +3 microcoulomb. So as you can see, they are all placed at the corners of a triangle. So let's calculate the electric potential energy for this system of point charges. In doing so, we have to consider pair by pair of point charges. Let's call this pair pair 1, 2. This pair right there is pair 2, 3. And the last pair is pair 3, 1, because you have the third charge and the first charge. Now each pair will contribute a term that look like this. K, which is a constant that we saw in Coulomb's law, 9 times 10 to the power 9. The SI unit of which is Newton meter squared per Coulomb squared. The product, the strength of the two charges in the pair, let's say in 1, 2 pair is Q1 and Q2, over the distance between the two charges in a pair. So in this case, let's call that distance R1, 2. So R1, 2. And so on. So the other pairs will have similar terms to them. So this is the term for this pair. R2, 3 is that distance right there. And the last term, this term right here, is for that pair. So K, Q3, Q1 over R3, 1. So R3, 1 is that distance right there. So let's write down the numerical value. So K is K. All the terms contains that K, so we can take that out of, we can factor that term out. So for the first pair 1, 2, the charges are -1 microcoulomb and +2 microcoulomb. So the product of Q1 and Q2 will be -2 times 10 to the power -12. Because microcoulomb is 10 to the power -6 coulomb. So 1 microcoulomb is 10 to the power -6 coulomb. From Pythagoras' theorem, R12 is 5 meters. Because this is 3, this is 4, so that has got to be 5. So divide by 5. Likewise, for the 2, 3 pair, the product of the two charges is 2 microcoulomb and 3 microcoulomb. So that's going to be 6 times 10 to the power -12. The distance between them is 6 meters. So this is 3, and that is 3, that's 6. And the final contribution, the 3, 1 pair, the product of charges is 3 microcoulomb and -1 microcoulomb. So that's going to give you -3 times 10 to the power -12 over the distances again, 5, due to Pythagoras' theorem. And that's it. And when you do the sum, you end up with 0 joules. And that is the electric potential energy for this system of point charge. Let's look at the second example. You have a system of 4 point charges, Q1, Q2, Q3, and Q4. They are all arranged on the corners of a square with a side 4 meters. And we want to determine the potential energy of this system of point charges. Now the possible pairs, there are 6 of them. The first pair is pair 1, 2. These two guys. The second is 1, 3. So 1 and 3 is that. 1 and 4. That means that. 2 and 3. 2 and 4. So that is the fifth one. And finally 3, 4. So there are 6 pairs. So let's write down one by one. Let's begin with 1, 2. So 1, 2. So let's factor the k out. So the term is Q1 times Q2. So minus 1 microcoulomb and 2 microcoulombs. So that's minus 2 times 10 to the power minus 12. The distance between them is 4 meters. So that is the first term. The second term is 1, 3. So the distance between charge Q1 and Q3 is square root 32 by Pythagoras theorem. Q1 is minus 1 microcoulomb, Q3 is minus 3. So when you add them, when you take the product, you get 3 times 10 to the power minus 12. The distance between them is square root 32. The third is the 1, 4 term. So the product of the two charges is plus 4 microcoulomb and minus 1 microcoulomb. So that's going to give you a negative term. Negative 4 times 10 to the power minus 12. The distance between them is 4. Next, term 2, 3. The product is minus 6 times 10 to the power minus 12. The distance between them is 4. So that's done. 2, 4 is that. The product of two positive charges, 2 and 4 microcoulombs, so that is 8 times 10 to the power minus 12. The distance between them, like before, square root 32. That is the length of that diagonal distance. And finally, 3, 4. So the product of the charges is minus 12 times 10 to the power minus 12. The distance between them is 4. And that's it. So calculating this term will give you minus 0.0365 joules for the potential energy of the system. The second form of electric potential energy involving point charges is the electric potential energy of a particular charge situated in an electric field due to other point charges. So in the arrangement below, you see 4 point charges, Q0, Q1, Q2, and Q3. R1 is the distance between Q0 and Q1, R2 distance between Q0 and Q2, and R3 is the distance between Q0 and Q3. What we want to calculate is the potential energy, the electric potential energy of this charge Q0, sitting in an electric field created collectively by Q1, Q2, and Q3. So whenever you have a charge sits in an electric field, in an external electric field, it would have its own potential energy. That is exactly what we want to calculate for Q0. From our previous video, you may recall that potential energy of a particular charge sitting in an electric field is given by that strength of that charge, Q0, in this case it is Q0, coulomb, let's say, times the potential at the point where Q0 is, the electric potential at the location of Q0. The potential at Q0 is created by 3 charges, Q1, Q2, and Q3. The expression for electric potential is given by the following. Let's do term by term. Let's do potential created by Q1 first. So it's KQ1 over R1. Next, potential created by Q2 at Q1 is KQ2 over R2. And the third contribution comes from Q3, KQ3 over R3. So substituting this expression in here, we obtain the electric potential energy of that charge Q0 sitting in an electric field created by other charges, Q1, Q2, Q3 in this case. Note that sometimes we can compactly written this expression in terms of sum So sigma is a sum notation, summed over terms Qi over Ri. So in this particular example, this represents these three terms. So let's go back to the same triangular point charge system that we encountered before. Now we want to calculate the electric potential energy of Q1. So Q1 is this charge right there. It's sitting in an electric field created by Q2 and Q3. So according to the formula that we have just written down a few minutes ago, the compact formula, sum over Qi over Ri terms, we get the following. So Q1 is minus 1 microcoulomb. So minus 1 times 10 to the power minus 6 K, which is a constant. And so in this particular case, there will be two terms in the sum. One due to this, the other one is due to that. So the potential created by Q2 at Q1 is K Q2, which is 2 microcoulomb, 2 times 10 to the power minus 6, over this distance right here, which is 5 meters, because this is 3, this is 4. By the Pythagoras theorem, that diagonal distance is 5. So over 5. Now the second contribution is due to the potential created by Q3 at Q1. So that's going to be K Q3. Q3 is 3 times 10 to the power minus 6. The distance is again 5 over 5. Only two terms in the sum. And you get minus 9 times 10 to the power minus 3 joules for the potential energy of Q1 sitting in an external field created by Q2 and Q3. We want to note two things here. The first thing is whenever you calculate electric potential is a scalar given by the following equation. So this is the electric potential created by some charge Q at distance R. And since it is a scalar, you don't have to take any components or anything like that. So this is the equation that we use here and there. The second thing to note is in our video on potential energy previously, we stated that potential energy must be set to 0 at some point. So for electric potential energy of a point charge, the potential energy is set to be 0 at infinity, hence the term that looked like that. So in this example that we have just did, if Q1 is located at infinity, at an infinite distance from Q2 and Q3, then it would have a 0 electric potential energy. If you find this video useful, please like, share, and subscribe for notifications on future videos. Thank you for watching.